Welcome back to PC1 for the first AMA of 2025, and we are off to a flying start. Our pioneering Production Centre 1 now has the capability to produce every component for GT50 and HX50 under this very roof, and it feels pregnant with something beautiful. Our composite laminating facility is now sealed, clean, and ready to produce composite parts for HX50. From raw materials delivered to goods inwards, these materials are then stored under strict temperature and humidity controls. Each composite ply is then precisely cut on our all-new composite ply cutting machine. Laser alignment is then used to place every ply into the tool accurately every time. Laminated parts then flow seamlessly from the laminating facility into our whole aircraft oven. Each component is precisely cured using our digital cure control system. Components are then demolded and prepped for paint before receiving their final paint finish. The painted airframes are then moved to the final assembly area. With all of the construction now complete, we've cleared the space for all of the structural test rigs and our ground test area. Our Precision Aerospace Casting facility has been online since January, giving us an end-to-end capability to cast all aerospace casting materials, from high-grade structural aluminiums, alloy steels, to, of course, super alloys. We can produce investment patterns using wax injection molding or modern 3D printing. We can produce block and shell molds for all aerospace cast materials. We carry out wax burnout and mold preheating, and air, inert environment, and vacuum investment casting. Everything you need to turn raw material into precision cast components for GT50. To meet the demanding GT50 program milestones, we've added this vast Multus combined machine turn center. Our precision EDM machine is now online and ready to cut cooling slots in turbine blades. We've added a state-of-the-art micro-machining center to produce fuel spray nozzles, hydraulic control valves, and fuel control valves. Our fully calibrated metrology lab is now actively policing everything we make. We've commissioned our high-speed test rig, which enables us to test the starter generator system electrically, mechanically, and environmentally. And with the rig fully commissioned and the prototype starter generator in hand, we've now been able to commence a detailed and comprehensive program of testing across a whole range of physical properties of the device. We've started by electrically characterizing the system, allowing us to tune the control algorithms that run on the power management unit. We've also managed to fully statically and dynamically balance the system, complete all of the alignment between the starter generator and the prime mover, and then we've run the starter generator in generator mode all the way up to 40,000 RPM, and we've run the starter generator in motor mode all the way up to GT50 ignition speed. And I have to tell you that the first time we ran the starter gen up to 40,000 RPM, pretty much everybody that's been involved in the design of the starter generator, the electrical team, the mechanical team, were all in here like a bunch of nervous first-time daddies, waiting to see if the thing was going to work, if it was going to hold together. It was a real moment in the program. Our compressor design has been both aerodynamically and mechanically mature for a number of years now. However, as other areas of the engine evolve and develop, that itself pushes changes back up to the performance requirements for the compressor itself. Over the course of the last month or so, we've subtly refined the design of our compressor to take account of the evolving needs of the engine. We've improved the performance of the compressor, increasing the mass flow slightly, improving the efficiency by a couple of percent. We've improved the surge and stall margins, and we've managed the axial loads that are generated by this on the thrust bearings that hold the whole gas generator rotor in place in the engine. We've also optimized the production process to minimize the machining time while reducing the overall tool wear that we encounter while making each and every one of the compressors. And we've developed specialist polishing procedures to squeeze every last little bit of efficiency out of the impeller that we possibly can. Another area of the GT50 engine that has received extensive development attention over the last 18 months or so has been our annular combustor, and this work is now finally starting to bear fruit. The annular combustion system is a complex arrangement of superalloy sheet metal components that provide film cooling to maintain the metal temperatures at acceptable levels and contain the entire combustion process while mixing the air and fuel and then diluting the products of combustion and feeding them smoothly into the turbine. The resulting geometry necessary to do all of these things is extremely complicated, and over the course of the last 18 months or so, you've watched us perfect every element of the manufacturing process to be able to produce these complicated systems. You've watched us laser cut and roll rings to form the inner and outer annulus, laser weld rolled strips into rings and qualify the strength of those welds as delivering parent metal properties. You've watched us develop the tools and processes to form roll the overlapping profiles of the combustor, delivering film cooling over the gas-washed inner surfaces. You've watched us develop specialist equipment to expand form rolled rings to the correct diameter and roundness for assembly. You've watched us develop the assembly tooling and precision laser welding processes to assemble the unit as one. Then either CNC drill or laser drill the 1,800 cooling holes necessary to balance the flow of compressor delivery air into the combustor to deliver stable, efficient combustion. And only when you've done all of those things can you build the very first GT50 annular combustion system. What I've got in my hands here is the very first annular combustion system for GT50, a culmination of 18 months worth of process development work and design work to deliver a small, lightweight, inexpensive combustion system for our pioneering general aviation turbine engine. What you can see on the back of the unit here is the 12 individual swirler and fuel injection ports that promote a uniform distribution of fuel and combustion products around the annular combustor. When you look on the outside, you can see the 2 ports for the igniter plugs, the primary and secondary dilution holes that provide the key zones in which the combustion reaction takes place, and then the finer cooling holes, the film cooling holes that provide the cooling film of compressor delivery air over the hot gas-washed surfaces of the inside of the combustor itself. Looking inside it, you can see the gooseneck feature that turns the flow back on itself towards the nozzle guide vane and then through the turbine stages, delivering the 500 horsepower that GT50 produces. What we've got here is a 3.5 kilogram annular combustion system manufactured by our vertically integrated manufacturing processes right here at PC1. Although the development of these processes has taken a little while, in reality, with all of the tooling and equipment now in place, we can produce one of these combustors from receiving raw materials to a finished assembled combustor in around 2 days. Welcome to the Hill Precision Casting Facility. Here, we cast turbine blades, nozzle guide vanes, engine casings, and internal core structural components from a wide variety of high-performance aerospace alloys. The investment casting process involves the following key stages. First, we create a wax pattern using conventional injection molding techniques or modern rapid prototyping. We then create a ceramic mold using either block molding techniques or shell molding from a ceramic slurry. We then burn out the wax pattern from the ceramic mold, leaving a void to fill with molten metal. We then heat the ceramic mold to near the melting point of the metal to be cast. We can then melt the metal, usually under vacuum or inert environment. The superheated molten metal can then be poured, again under vacuum, to fill the mold. The molten metal is then cooled at the correct rate to freeze and lock in the required crystal structure. Once frozen, the cast part is broken out from the ceramic mold and cleaned. The running system can be removed, the casting inspected, and then subjected to its final heat treatment to obtain the required mechanical properties. Nozzle guide vanes represent a uniquely difficult challenge for casting processes. Not only are the blades extremely closely spaced and overlapping, they're mounted in inner and outer platforms that pin them together, which often contain complex hook features to secure the nozzle guide vane in the engine. On top of this, each individual blade itself is hollow to allow cooling air to pass through the center of the blade. These voids need to be created with ceramic cores, which must be cast into the mold and then bleached out with an array of very unpleasant chemicals. Since coming online, in January, Mark and the team have been developing the plethora of processes necessary to be able to cast these complex parts. And here is the very first GT50 nozzle guide vane cast in the PC1 casting facility. So these inner and outer rings are generally cast oversized and then machined back. You can see each of the blades formed as an integral part of the casting. And in this prototype version of the nozzle guide vane, we'll actually EDM the cooling slots into these to avoid the need for cores. In production, the cores will be integrally cast to make the process more efficient and to give us a more refined cooling channel. Another crucial component that we've manufactured for the first time over the last couple of weeks is the cast bearing housing that supports the rear of the gas generator rotor shaft. This crucial component connects the secondary air system, the lubrication system, supports the bearings, the squeeze film damper and the spring bar, and connects the outside world with the core of the GT50 engine. Of course, the most important and probably the most difficult part of making any turbine engine is the manufacture of the high integrity rotating turbine blades. Now we can produce those too. GT50 uses superalloy polycrystalline blades which provide a nice balance between high performance, long life, reliability and cost effectiveness. While the geometry of the turbine blade castings themselves is somewhat simpler than some of the other shapes that we've had to learn how to cast, the integrity that's required and the quality of the castings needed for these components is absolutely second to none. Now we can do that too. We've created our very first GT50 high pressure turbine blades, and here is one of them. In order to ensure that every part of the turbine blade, including the incredibly thin trailing edge, are adequately filled and free from pores and defects, then we've had to develop an advanced feeding and running system to get the molten metal into each of the blade cavities when we cast these blades in batches. Mark and the team have perfected this over the last few weeks and are now able to reliably fill blade molds with high integrity superalloy material. In terms of the next steps to take these blades and get them to the position where we're happy to put them into an engine, the next thing that we have to do is to switch out the rapid prototype patterns for wax injection patterns to get an adequate surface finish from an aerodynamic perspective. We can then characterize the shrinkage of the casting process and correct for that so the parts come out at exactly the size we need. And then we can go on to calibrate the cooling rates and the heat treatment to refine the mechanical properties to exactly what we need for performance in the engine. In summary then, we've built the first starter generator and successfully completed the first phase of mechanical, electrical and control system testing. We've validated the in-house designed power management unit hardware on the test rig. We've built the first casings, drive shafts and bearings for the speed reduction gearbox. We've validated the first half of the production gear manufacturing process. We've now completed 80% of the components for the speed reduction gearbox test rig. We've completed the first GT50 annular combustion system. We've completed the design for manufacture on the first production intent fuel injection nozzles, sourced prototype parts for testing and acquired the production equipment for series production of them. The Hill Precision Casting facility is now online and has cast the very first GT50 turbine blades, nozzle guide vanes and bearing housings. We've ground the first fir tree roots for GT50 turbine blades, completed full geometric inspection and cleared all tolerances. GT50 is coming fast and more importantly on budget. And at a time where everybody else's prices are rising dramatically, ours are robustly controlled. Vertical integration works.